Hello, everyone, and welcome to this evening's Nuclear Masterclass, looking at astrophysical objects and how nuclear physics plays a role inside them. My name's Dr. James Cubiss. I'm a lecturer at the University of York, and my research involves measuring the shape of atomic nuclei using a combination of lasers and measuring the decay radiation. So I'd like to welcome you all for joining, not only on behalf of myself, but the whole team delivering this session. Before we get started, there's a couple of technical details I'd like to go over. First of all, please everyone make sure that you've got a nice cool glass of water near you, particularly those in the UK who are experiencing unprecedented temperatures. It's good to keep safe and hydrated for this evening's session. We have an hour of talks, great talks and questions to get through. If you're watching live, remember you can ask questions throughout the talks, not just at the end, using the Q&A function, which you'll be able to find at the bottom of your Zoom screen. Subtitles are also available there. You just have to click on the CCC live transcript button in order to be able to see them. If you have any technical issues and you find yourself disconnected from the session, you're always able to rejoin using the link you were originally sent. And please remember, this webinar is being recorded, so if you are disconnected and for whatever reason you cannot reconnect, the recording will be available for you over the coming weeks. So let's get back to the masterclass. As I said, this evening's session is looking at the role nuclear physics plays in the heart of astrophysical objects and how this gives birth to the chemical elements you and I are made of and the world around us. So this evening we've got two speakers, a specialist in astrophysics and another specialist in nuclear astrophysics. So for the first presentation, I'm going to welcome Kate Womack from the University of Hull. Kate is an astrophysical PhD student at the university whose her research focus is on the chemical evolution of galaxies. So she's going to be giving us a whistle-stop tour on space and the chemical elements. So Kate, over to you whenever you're ready.
Brilliant, thanks James. I will share my presentation. Hi everyone. So as James said, my name is Kate, and I'm going to be talking to you today about the stellar origins of the chemical elements. So essentially a whistle-stop tour of both the periodic table and space. I'm going to start with this. This is the classic Carl Sagan, "We are made of star stuff" quote. And as you can see, it's maybe been a little bit cringified. These are two posters that I got from Pinterest. But it's still entirely true. Everything around us started its life in space. You know, that's me, that's you, that's the chair I'm sitting on, the laptop I'm talking to you through. Every atom that makes up everything started its life in a star. And there's a lot of things, I think, especially with what I do with astrophysics, but just in physics in general, that when you think about it for too long can make you feel really quite small. And this is the one that really does it for me. But obviously today I'm going to be talking to you about the elements. So let's show you the elements. This, as I'm sure you're all aware, is the periodic table, but obviously with a little bit of a twist. So here we're placing, each element is given a colour based on the type of event or type of star that makes it. So you can see we've got the hydrogen and the helium from the Big Bang. We've got sort of everything in this top half made from explosions, so exploding massive stars and exploding white dwarfs. And then everything in this bottom half from our major neutron stars and our dying low mass stars. So as you might have guessed, I'm going to talk to you about these four things. So I'm going to tell you about exploding massive stars or core collapse supernova. This is the Crab Nebula. So this is a remnant of one of these exploding massive stars, which was observed in 1054 by Chinese astronomers. I'll tell you about exploding white dwarfs, or what we call type 1a supernova. This is another remnant of one of these events. This is Tycho's supernova, which was first observed in 1572. I will talk to you about dying low mass stars. This is a red giant. Our sun will eventually become a red giant, and when that happens, those layers are going to expand right up to the Earth and eventually even beyond. And I'll talk to you about neutron star mergers, not only how they're useful for the production of the elements, but also about that gravitational wave detection back in 2017 that confirmed their existence. So let's start with explosions and talk about our exploding massive stars, our core collapse supernova. These are the really big stars. These are the stars that have masses 8 times the mass of the sun or more. So these are our really big objects. Now, as you can imagine, these objects are quite hot. There's a lot of pressure, it's quite dense. And so that means we have really violent reactions. And these violent reactions lead to quite short lifetimes for that star because we've burned through the fuel that star has got really quickly. And when we burn that fuel, we get this sort of onion shell structure of the elements that we see in this top picture. So you can see we've got the hydrogen, helium, carbon, oxygen, neon, silicon, and eventually right in the core, we've got iron. Now, once the core becomes rich with iron, the star runs out of fuel. There's no longer any burning, any nuclear reactions going on in the core. And so that means there's a lot of gravitational pressure, which causes that star to collapse. And boom, we have a core collapse supernova. But stars don't just die and do nothing. When stars die, the elements that they make throughout their lives get put back into the galaxy that they're in, back into the gas that surrounds them. And so in this case, when we talk about core collapse supernova, these stars enrich the galaxy with what we call the alpha elements. These are things like oxygen, magnesium, silicon, some of the intermediate mass elements as well, things like aluminium, and then a little bit of iron as well. And obviously it's really cool that these stars make these elements, but another thing that makes these objects quite cool is that these are the ones that become neutron stars and black holes. These are the objects that end up, ending their lives with something quite exotic and quite interesting. But then we have our other option for explosion, which is our exploding white dwarfs, and we call these our type 1a supernova, and they explode in quite a different way. So first of all, what is a white dwarf? Well, a white dwarf is what's left over when an average star ends its life. So a star like our sun will end its life as a white dwarf, and it's essentially just the leftover core of the star. So it's just what's left over, and that is made of carbon and oxygen. But these stars don't tend to be on their own, they tend to be in binary systems. So you'll have your white dwarf, and then you'll have maybe a star in the main sequence or a red giant star in a binary system with it. And this white dwarf will use its gravitational pull to steal material from its companion. It will start to take material from the other star, and this causes the nuclear reactions on that star to start up again. But this takes quite a long time for this to happen. These stars are quite low mass, which means they live for a really long time. So this star has to go through all of its first life before it gets this second life where it starts stealing that material again. So it takes about 1 billion years for a type 1a supernova to occur from sort of birth of the star to death. But eventually it will steal so much material that the star can no longer support itself. And this happens at a critical mass, which is about 1.4 times the mass of the sun. We call this the Chandrasekhar limit. And when this limit is reached, the star will explode, and it enriches the galaxy with what we call the iron group elements. So these are the elements on the periodic table between titanium and zinc. So these ones coming along here, this is the iron group. And as you can see, with our explosions, we've covered sort of this top half of the table. But what's going on at the bottom half? How do we make these elements? Well, we make these elements with something called neutron captures. And neutron captures are really useful because neutrons, as the name would suggest, are a neutral particle. And this is great for us because if we think about something like iron, iron has a really positively charged nucleus. There's lots of protons in that nucleus. And so if we try to make something heavier by adding something with more protons, there's going to be a repulsion because that's two really strong positively charged things. It's like trying to add two north poles of a magnet together. They're going to repel. But if we use neutron captures, neutrons have no charge. So we can add them to make heavier and heavier elements. And there are two ways that we do this. And I'll talk about both in this next part. So let's first talk about our dying low mass stars. So these are our dying low mass stars, or what we call AGB stars. This stands for the asymptotic giant branch. And essentially what this means is if we've got this red giant over here, so this is your stage after the star has been on the main sequence. This is a star who, if this is our sun, its layers have expanded as far out as the Earth. So when our sun reaches this phase, the Earth will be engulfed in the sun's layers. But with an asymptotic giant branch star, with an AGB star, there's more mixing going on in the center. And so what this means, and more reactions going on in the center as well. So what this means is that the layers can expand even further out, and eventually our sun will engulf the whole solar system. Like it says here, expanded outer layers of between 1 trillion and 100 trillion kilometers. And as much as that's cool and really interesting, what I'm more interested in is what's going on deep in the center, where we're making elements like strontium, yttrium, zirconium, barium. And we're doing this with the S process. This stands for the slow neutron capture process, which is what I'm going to talk to you about now. So that's one of the ways we capture neutrons. And before I show you how it works, I'm going to show you this. Now, I'm sure you're familiar with this already. This is the nuclide chart. And the nuclide chart essentially places each isotope depending on how many neutrons it has along the bottom and how many protons we have up the side. And we have our stable isotopes running along the middle. And so if we take a zoom in on this and look at the region between krypton and zirconium, I'm going to show you the path that the S process takes with these yellow arrows. So you can see we're starting with krypton 82, which, as you'll note, is stable. Obviously, if it's stable, we're not going to go through any sort of radioactive decay. And so if there's neutrons around, we can capture one and make krypton 83, which is also stable. We make krypton 84, which is also stable. So we make 85, which is unstable. And then we can capture and make rubidium, which is stable. Rubidium 86, unstable, decay. And you can see how if there's neutrons around, we can slowly and steadily build up those heavier and heavier elements. And this is the S process, the slow neutron capture process. Our other option for neutron captures is the R process. And this is what's occurring in merging neutron stars. Apologies. But before I talk about the R process, let's first talk about what neutrons actually are. So a neutron is a very compact, very dense ball of neutrons, about 20 kilometers in diameter. And within that 20 kilometer diameter, we're packing about 1.4 times the mass of the sun. So imagine you've got that much mass in a diameter that small. And I've done a little illustration here. I'm based at the University of Hull, which is where I've put my little pin. And if you're familiar with the area, you'll see that a neutron star would only just get you to Barton, just across the river, and just a little bit past Beverley, which is a town outside of Hull. So if you know the area, you'll be familiar with this, but it's just to really show you just how much mass we're packing into a really small space. And as I said, these neutron stars are remnants of those core collapse supernova. And when they merge, it's a really highly energetic event. And I'm going to show you this now. So for a merger to occur, obviously, we need to have two neutron stars. And these neutron stars are orbiting around each other. And as they're falling into each other, they're interacting gravitationally. So what this means is that they're interacting via gravity, and when they collide, they release those gravitational waves that were detected by LIGO. And as you can see, these mergers are also really energetic. You'll see once they merge, you can see how hot, how energetic that merger is. And it's these really hot and really energetic conditions that allows for the R process to occur. So we've got lots of energy and lots of neutrons around, which means we can do the R process. This is the rapid neutron capture process. And when we do this, we make things like europium, platinum, gold, all of those precious metals. But how exactly does the R process work? Well, we've got this little GIF, so this will keep sort of repeating over while I talk about it. But you can see here we've got the stable isotopes this time in white, and then the sort of color scale we're seeing is the isotopes that we're making with the R process. So you can see immediately there are so many neutrons around that we're in fact making things that are really, really, really unstable. And not only that, we're also making elements that don't have any stable isotopes at all, the elements that exist right at the top of the nuclide chart. And it's only when those neutrons get turned off that everything sort of starts to be able to decay back towards stability, like we see at the end of this GIF. And that is how the R process works. We make really unstable things and we worry about decaying them later. And there you have it. That is our whistle-stop tour of the solar system and the elements. As you can see, we've now covered most of this periodic table. So what have we learned? Well, we've learned about core collapse supernova, these exploding massive stars. and how they build up those elements in that onion shell structure before it explodes and releases those elements into the galaxy. We've learned about type 1a supernova and how they're able to steal that material from their companion and reach that Chandrasekhar limit that's so important. We've learned about dying low mass stars, and we've seen how those layers expand really, really far, but actually how we're doing really interesting nuclear physics with the neutron captures deep in the center. And we've seen about merging neutron stars. And we've seen how not only is it cool for cosmologists looking at those gravitational wave detections, but it's also really interesting for people like me who are interested in the elements to finally understand where those heavy elements come from. And it's at that I will hand back over to James, and thank you all for listening.
Excellent. Thank you so much, Kate, for that really nice overview of the origin of the chemical elements in the galaxy around us. So we got a couple of questions from the audience. The first one: could there hypothetically be another galaxy or universe with our periodic table if it originated by the Big Bang like ours did? Or is the periodic table determined by other factors?
I mean, another galaxy, definitely. You know, there are plenty of galaxies in our universe that are star forming and will make stars in exactly the same way that ours do, and therefore make the same elements that ours do. In terms of another universe, I don't know. Nobody knows. I mean, the best guess for our formation of the universe, the thing that we know is that there was this big bang. So I guess it's plausible another universe would start the same way if ours did, but how it would proceed from there, I don't know if anyone could tell you that.
Yeah, I suppose it's a question for the philosophers. We can only really say what the laws of physics are within our own universe. So your imagination can run wild with what else there is out there. Another question. So we got two which are the same. Why are technetium and promethium grey on the periodic table?
Yes, so that's a really good question. The reason for this is that technetium and promethium actually don't have any stable isotopes. So we can make them in stars through the processes that I've talked about, but there are no stable isotopes. So eventually, through decay or whatever, any other processes, eventually they'll become something else. And so it's not likely that we'll find them here on Earth. They don't exist here on Earth, but we can and do make them in space. Yeah,
so I suppose there'll be, if you were really interested, you would look at the neighbors and you would presume they were produced in the same stellar environment, but just they decay away to
absolutely. And the interesting thing about technetium as an element is that if we observe that on the surface of a star, we know that there's active S process going on in that star at the time that we observe it, because we know it has to decay to something eventually.
So it's a real spectroscopic fingerprint of the S process. Very nice, very nice. Okay, excellent. So there's plenty more questions in the chat, but we'll revisit those at the end of the session. So I'll thank Kate again now.
Very much.
Everyone in the audience, please, if you have questions for Kate, please keep posting them, because we're going to have an extended Q&A session after our second speaker, who I'll now introduce. So we've got Dr. Christian Diget now speaking to us. He's from the University of York, so one of my colleagues. His research involves nuclear physics of stars, so looking at the reactions that go on in the heart of stars. And he also develops new detector technologies for medical applications. And he'll be speaking to us this evening about how to bring astrophysics down to Earth. So over to you, Christian.
Thank you so much, James. I will just share my screen. Okay, so thank you so much. And I will talk to you, as James was saying, I'll talk about how we take astrophysics down to Earth. So obviously, all of these reactions that Kate was talking about happen far away in stars, or a little bit far away in our star, the sun. But in any case, if we want to study these reactions, we need to study them, take them into a laboratory. And that's what I study. So that's what I will talk about here. I'll talk somewhat about reactions that happen in the sun. I'll talk a little bit about reactions, quite a bit about reactions that happen in stellar explosions, and a new type of explosion that Kate hasn't even talked about. I'll talk about how we use accelerators to study these reactions here on Earth, and over to the right here, how we use some of the modern nuclear detectors that we can use to detect the reactions that we're studying. So that's the tour that I will take you on. As I said before, I'm starting off from the point that where Kate left us with the origin of all of the elements. So it's the same thing that we're studying. It's just that we're studying here the reactions individually that takes us through this process. How does nuclear physics help us there? So the one key message that we need to remember is that when we take nuclei and we convert them into other nuclei, it's fundamentally what was in medieval times called alchemy. You need nuclear accelerators to do this, so it didn't really work at the time. But what we do is in effect the same. We take one type of atom and we make another type of atom. That's what the sun is doing. The sun is making helium out of hydrogen, and in the process, it's converting some of the mass of the hydrogen into energy, and most of the mass goes into the helium. So just to give you an example of this, you've probably seen Einstein's famous E equals mc squared formula before. But what you should remember there is that c, the speed of light, is a huge number. And we take c and multiply it by itself, so we take it squared. So c squared is massive, right? I've written it out here. I've taken c squared, multiplied it on by 1 kilogram. I don't worry about all of the numbers here. We call it 3 times 10 to the 8 meters per second in rough numbers. And you square it, you multiply it by a kilogram, and you get, what's that? 90 million billion joules. You can look up what that million billion is called. Must be. In comparison, you use about 19 billion joules per year of electricity, if you include factories that support you, etc. So these are massive energies. And therefore, even if only a tiny fraction of the energy is converted, the mass is converted to energy, free energy, light, heat, it's still a massive number, right? So even if we just take 1 gram of material and we convert 1,000th of the mass into free energy, these are still huge numbers. We're still talking 90 billion joules from a single gram of hydrogen. So this is what's going on in the star. This is what's powering them. We're interested in that clearly, but we're also interested in how do we get elements out of these. So I'll take you through now a different example. It's also hydrogen fusion, actually. That's why I wanted to start off with the sun. But in hydrogen fusion, we have, in this case, a neutron star, again in a binary system, just like the binary systems that Kate was talking about, except now it's a neutron star next to another big star doing it as part of its stellar life before it blows up. But this neutron star is really compact and it has a huge gravitational field. So any material that gets close to it gets sucked up. And that's what you can see over here to the right with the accretion disk over here. That it steals the hydrogen from its companion, and that hydrogen will fuse to helium, but it's through a different process. It's a catalytic process where, for example, you can add the protons onto carbon and other light elements. It's the same thing you need to do. You need to add 4 protons together, make 2 of the protons decay via a beta decay. It's a beta plus decay. You need them to decay to neutrons. And then in the end, you need to let the final nucleus emit an alpha particle or alpha decay from its very energetic state that you produce. That's how it works. And I'll take you through some of the details now. So if you take a look here to the right, you can see this is again a snippet of the nuclei chart. Now I've got the darkest elements here, are isotopes here, are the stable ones. So for example, you can start at carbon-12. And one way you can do this cycle is to absorb a proton. You move up the chart. You absorb another proton, you move up the chart. You can beta decay and you move diagonally down towards stability. In this case, we can absorb another proton, beta decay once again, and then absorb a proton. And now we've absorbed 4 protons in total. So actually, in this case, we might let the oxygen, which we could produce in a really energetic state, energetic enough that it just emits an alpha particle. So that's a proton absorption on nitrogen-15, followed on by alpha decay of the oxygen-16 in its very energetic state. And an alpha particle taken out of oxygen takes you right back to carbon-12. So oxygen-16 has got a mass of 16. You take away the 4 from the helium, and you get back to carbon-12. So this is one of these cycles. There are many different cycles up here. But one of the really interesting aspects about this is that you get stuck in these catalytic cycles. That's why they're catalytic, because you always get back to where you started in some way. There are different starting points, but you always tend to cycle back one way or another. So if you want to escape from this reaction mechanism, it turns out that proton absorptions are not enough. So in order to actually escape, we need to add not a proton, but one of the alpha particles that were produced earlier in this cycle. So someone in this cycle has produced an alpha particle, a helium nucleus, and we can now fuse that with one of these so-called waiting points. There'll be a lot of oxygen-15 waiting in this cycle, because oxygen-15 has quite a long half-life among these. And we therefore have some oxygen-15. If we can add the helium to it, we can get up to neon-19, and that way we can escape. And the interesting thing about this is that this secondary proton absorption that starts off at neon-19 it's called the rapid proton capture, because it's really rapid. Because when we have so many protons, it just whizzes up the chart from there on. And that process, again, converts protons into something that has less energy than the protons had. And therefore, we get a lot of energy out. So dependent on how effective this oxygen plus alpha fusion is, that will determine a lot about how these explosions take place. And you can see a simulation here of 2 different types of, 2 different assumptions of this simulation of an explosion on this neutron star. And you can see the dashed line here is just tweaking the rate at which alpha capture or helium fusion can happen onto oxygen-15. So that's what we're interested in studying. And I'll show you some details of how one could study that. So what we do in order to take this down to Earth is that we need to fuse the oxygen-15 with the helium. So we need to smash those 2 together. Oxygen-15 is radioactive, it's unstable. So the most practical thing is to make oxygen-15 as a radioactive ion beam, as we call it. So we send them, we accelerate them, and we send them into a target, as you can see here, and we need to study then everything that comes out of the reaction that you see. We can do that in many different laboratories. I've given you a few snapshots of different labs that I have worked at. I'll show you a little bit more about the top one that's in Vancouver called Triumph. And that's where I worked just before I came to York. Before that, I did some work at a laboratory in Michigan, where they're now building a new rare isotope facility called FRIB. That's in the middle here. At the bottom, we've got a laboratory in Finland. So they're scattered all over the world. And this is a place that I went to as part of my first research studies as a PhD student. And actually, the lab that I'm hiding here in the background to the right, I'll show you a little bit more about that. It's in France, it's called Ganil. And again, this is a radioactive isotope facility where we produce radioactive isotopes and accelerate them and smash them into a target and study what happens. So I should probably have mentioned CERN, but you've already heard about CERN. Actually, CERN was also my way into nuclear physics, unsurprisingly. But these are the labs that I have mostly studied at. So let me show you a little bit more about an exemplar. This is at the facility in Vancouver I mentioned, called TRIUMPH. They have a massive called cyclotron where the acceleration is by circulating the ions, in this case the protons, in a big cyclotron. You can see a person in here doing maintenance on the cyclotron, so it's a massive beast. Those protons are used to smash into a target and produce the radioactive isotopes that we study. Those radioactive isotopes are then sent through an accelerator. I've got a picture of one of these at the bottom here. This is, in effect, these are electrical radio waves that we make in the accelerator, and the charged particle that we're accelerating, we make that ride, so to say, on a wave, just like a surfer. If you ride on the front of the wave, you're pushed forward. We do exactly the same with electromagnetic waves in these accelerators. The trick is to synchronize it, to make sure that the ion always rides in the right place on the wave. That's the tricky part about making these accelerators, and is why there's a lot of technical development going into how you design them. Lastly, you need to send it into a separator to study what's going on. On the right here, you can see here the beamline curving around, and there are bending elements here. This is an example of something called Dragon, which is this kind of separator. And in principle, this could be used to study oxygen-15 plus helium, making neon-19 and separating out all of the neon-19. It's so difficult to produce the oxygen-15 that actually we don't even have enough oxygen-15 to make that experiment work in the lab. So we have to find a different way where we can do it a little bit more indirectly. So what we do instead is that instead of fusing the oxygen-15 with helium, we fuse it with lithium, or we hammer it onto a lithium target. So I'll show you some details of this. Around this lithium target, you can see that, you can't really see it, but it's in the center of the setup here. We take that lithium target and we surround it by detectors, and I'll show you a little bit more about what those are, but that's what the setup looks like in a schematic. And I'll talk you through the different components. But the way this works, and that's quite a nice way actually, is that if you send the oxygen-15 onto a lithium-7, lithium-7 is like an alpha particle, a helium, and a tritium, and a triton, or a tritium nucleus. If you've got those two together as lithium, you can react with just one component of it. So we can get the oxygen-15 to interact with, fuse with the alpha particle in the lithium and produce the neon-19 that we're interested in studying. So now we need to detect everything that's coming out. We need to detect a gamma ray that's coming out of the reaction. We need to detect the remaining triton, which is emitted, and we need to detect the heavy ion that's remaining, the neon-19, just as I talked about in relation to the Dragon separator at TRIUMPH. So this is what the setup is. We've got a compact setup in here that detects the tritiums, the tritons. We've got a massive setup around it called Agatha, which tracks and detects all of the gamma rays around it. And we have a setup called VAMOS, which is a separator that separates all of the neon-19 out from all of the other reaction products that are produced. So it's quite a violent reaction, so lots of different reactions are happening at the same time. We need to find just the right reactions that produce just the right state in neon-19 and detect that using these three different components of detectors. So that's what we did. It took about 2 weeks to do that kind of experiment. And from those 2 weeks, we got about 20 terabytes of data. And from those 20 terabytes of data, we had 3 events that were just populating the right state in near 19 that we detected with full detection of the tritons, the near 19, and the gamma rays at the same time. So these experiments are really challenging, but it's also really quite enjoyable to see. And we were looking for these as they were coming in. We needed to do further analysis on it, but sometimes in these experiments, you are eagerly waiting to see whether is there another one coming in today. So that's quite exciting. We ended up getting 3. That's fantastic. And it turns out, as a result of that, we now know that it's even more challenging than expected for stellar explosions to fuse this oxygen-15 with helium. It's actually more challenging than we thought it would be before we did this experiment. And we can feed that back to stellar modelers. And actually, there are modelers right now in Barcelona who are using these models, these new reaction rates, to study what now goes on in these stellar explosions on neutron stars. So I look forward to seeing that. It's ongoing research. It's happening just now, but I look forward to seeing how that feeds into our understanding of the universe. So with that, just to recap, that I hope you've got a sense of how we can now use a combination of accelerators and detectors in order to study some of these reactions that happen deep inside stars or in stellar explosions. So with that, thanks for that, and I'll hand over to you, James.
Excellent. Thank you very much, Christian, for that overview of current experimental techniques and brand new, hot off the press results from one of your experiments. Scientific results very rarely get as fresh as that.
No.
The research still ongoing.
Yeah.
So a couple of quick questions from the audience. We got one. Well, with regards to this, I suppose it's when you were showing this diagram of the CNO cycle in action. Wouldn't the proton absorption be inefficient for the elements? Surely elements want to be more stable.
So yes, when you produce these nuclear isotopes, by proton absorption, if you take one step up in proton absorption, yes, you become unstable, and that would normally decay to the stable partner. That's what happens in the CNO cycle. That, for example, the sun will do a little bit later in its life. The slightly heavier stars have quite a lot of CNO cycle. The trick about the hot CNO cycle is that it's so hot and it's so dense in terms of the number of protons that we have, that actually you can overcome the slowest beta decays. So normally, yes, that's spot on. If you put enough protons in, if you put enough heat in, the protons can start to win. Okay, yeah, I guess it comes down to if you have enough energy and you don't break any of the laws of physics, the world's your oyster, really. Yeah, so it really depends on the scenario that you're studying. I chose one of the most violent proton explosions that I could think of. So it doesn't come. It's called X-ray bursts. I don't know if I said that, but it doesn't come much more violent than that. Basically, if you take a neutron star and if you add a lot of protons onto it, it gets really, really hot and it ignites, and then you can get this amazing explosion. Yeah, you need these real cataclysmic events. It is, yeah. Oh, impressive stuff. So we got another one. How do you synchronize the waves to move a particle in an accelerator? And whilst you're answering that, I'll remind the audience we're about to start the Q&A session after this. So please
keep submitting your questions for Christian and for Kate, and we'll have an open panel session. So I'll repeat the question just in case. How do you synchronize the wave to move a particle in an accelerator?
So there are two aspects of it. One is, so if you remember that accelerator, so it has different elements of acceleration, and you always make sure that when it goes from one element to another, so let's say it's got 4 or 5 here, when it goes from one element to another, you need the electric field to push it in the right way, right? That's basically it. You need to make sure that the electric field is synchronized such that a positive charge, it's typically positively charged these, that a positively charged ion is pushed the way you want it, right? And then it's accelerated a little bit more. So you need to make sure that it's synchronized. The first thing to do is to make sure that it comes in sync. So whatever goes before, you need the particles to be bunched up, and that bunch needs to come in sync with the radio frequency of this accelerator. So the way you do that in practice is that you have some sort of feedback from that, which tells you the timing of your radio frequency here, or it might change the timing of your previous accelerator. I think it's most normal to use it one step at a time. So you got that accelerator under control, then you seed it and send it into the next one. So you need to bunch it up, and you need to synchronize it coming in. The next part is that as these are getting accelerated, they go faster, right? That's the whole point. And therefore, you need the acceleration. You need the time. If they were identical elements, you would need the time gap to be less and less, right? That's really difficult to do because the RF that you want to feed in, the radio frequency wave, it's like a microwave. Of course, it has a fixed frequency. So you can't really do that. So the way they do it is to make these elements longer and longer as you look down the beamline. It's really, and exactly how much longer they need to be is about exactly how much can you possibly accelerate your ions from one step to the other. So, I mean, that design is, I couldn't do it, but there are people who can design that. There are fantastic engineers who can do that. I just look at the kit and marvel at it. So yeah.
Yeah, I think it's important to state that accelerator physics is its own field of research. It's
completely separate. Yeah, I'm not an accelerator specialist. I'm a detector specialist, but I'm not an accelerator specialist.
Yeah.
But they're cool, and we need to be able to work together as a big team, right? So it's about making the whole thing work as one, right? There are many tens of people working on making just one of these experiments happen.
Yeah, and I think it's also full disclosure. These things don't always marry together nicely. You can spend a whole day trying to get your accelerator and your injector to get in phase. So it's not that we put them together and suddenly you have this lovely Mexican wave kind of pushing along your particles.
There are very few accelerators like that which are plug and play, right? The only place where I've seen that is the modern accelerators that are put into hospitals, for example, for proton treatment. Those have to be operated in that type of environment, and we need to know that they work. So actually, those have been set up so that you turn the key and they work. Right? Yeah. But in every other case that I know in the labs that we work at, it doesn't work like that. It puts the boundaries a little bit more, I think.
Yeah. Thank you very much. So at this point, I'll invite Kate back into the session, and we'll do a bit of a panel Q&A. So I'll look back at some of the older questions and just start picking them out more or less at random. So on the chart that you showed, it shows that, I think this is Kate, it shows that some elements heavier than iron can be formed in exploding giant stars. Could you explain how that happens? What's really going on there?
Yeah, so it's a very astute observation. Some of the elements heavier than iron are formed in our exploding massive stars and our exploding white dwarfs. And this is still neutron captures. It's just that in these sites, we don't have the neutron density. We don't have the number of neutrons to get as far up the chart as we would in the other sites I talked about, the low mass dying stars and the neutron star mergers. So we can do a little bit of neutron captures and get things that are a little bit heavier, but not things that are really heavier. What's interesting about massive stars, though, is that, and what the stellar models are telling us, is that if we apply rotation and we have a massive star that's rapidly rotating, we have extra mixing then going on inside that star. And so that means we can do a little bit more of that S process. And so actually we can make some of those S process elements in those massive stars, but they have to be rotating quite rapidly. So yes, still neutron captures, but just not as many neutrons as we have in the other places.
Okay, interesting. That rotation is something brand new to me. So that's you know, even I'm learning. A lecturer in physics, I'm learning. Okay. Oh, here's a very good one. Is beta plus absorbing an electron or emitting a positron?
I'll take that one. Yeah. So beta plus technically is emitting a positron, right? The thing is that quite a few of these can either decay via emitting a positron or by absorbing an electron. So in both cases, you convert a proton to a neutron. You can see the charges still match up. Whether it's one or the other that win depends on the details of the nucleus. Generally, it tends to be that in the lower part of the charge, where they're not too massive, where the charges are not too high, beta plus decay tends to dominate, and the further you go up, the more likely it is that electron capture dominates. And it's very simple to explain, because in the big elements like gold, for example, where you've got a lot of protons in the nucleus, it also means that the innermost electrons are really compacted in the atom, and then you've got these shells, and the innermost electrons overlap a lot more with the nucleus for the heavy elements than they do for the light elements. So what do you need in order to get electron capture? You need the electron to interact with the nucleus. So therefore it happens for those electrons in those elements that have the best overlap between the nucleus and the electrons. So in principle, both could happen for most of these cases, but in practice, it's dominated by this, and then there's some energetics as well involved in it.
Excellent, thank you. Okay, another one perhaps for Kate. How do neutron stars collide? Shouldn't they be stationary and therefore they can't move?
Okay, so at this point, I'll say my field of study is galactic chemical evolution and not so much neutron star mergers. So this isn't going to be the most expert answer. However, here with the neutron star merger, you've got obviously two neutron stars. They're in a binary system. So they're orbiting around each other. And as they sort of move around each other, they're interacting gravitationally. And this is what's important, because it's that gravitational interaction that causes each of the neutron stars to lose momentum. And so they're able to start spiraling in towards each other. And it's that gravitational interaction and that loss of momentum that then means that they can merge. So that's my sort of non-expert answer, is it's that gravitational interaction that gets that merger. For a general binary system, two stars can be quite happy just sort of being in a binary system for all of their lives, and maybe at one point one will steal material from another and then another will steal it back, and so on and so forth. But it's this gravitational interaction that's really the special bit about the neutron star mergers.
Yeah. And I would also add there's very few objects out there in the universe that are stationary. In fact, it's very hard to tell whether you're stationary or you're moving. This is the equivalent, Einstein's equivalence principle, right? So you can think of this as being sat on a train with your bottle of water on the table in front of you, if you're lucky to get a table seat. The bottle of water isn't moving relative to you, it's stationary. But to an outside observer, you and the bottle of water are flying past it. well, if you're in Europe, 150 kilometers an hour on one of these fast trains. If you're in the UK at the moment, you're not going anywhere because none of the trains are running. But yeah, it's everything is really in motion and orbiting around some center of mass, and a lot of the times coming in together and colliding.
So, James, if I might just add one comment to what Kate, jump in and do that. So I did for different reasons actually, but I did a calculation this morning about how long it takes for these neutron stars to do. I used a fairly simple approximation, so take it with a grain of salt. But in that approximation, which is basically the energy is emitted by the gravitational waves, and there's nothing else going on. There's no deformation of it and so on. There's plenty of other things that actually would be happening. But if you do that, if you take the two neutron stars and you make them spin around each other at a distance of 100 kilometers, that they have quite a strong gravitational interaction, and this spinning in will happen within about a second. If you take them a lot further out, so you remember, so 100 kilometers, you remember Kate's picture of Hull. 100 kilometers would put the next one certainly a good way on the other side of York, right? So they're still they're still very close in an astrophysical context. If you take them as far apart as, say, roughly the radius of the Earth, a little bit more than that, that spiraling in time goes up dramatically. So it takes about a year for them to spiral in if they're about as far apart as a little bit further than the center of the Earth is from me. Now, if you take them at about, I think I got this right, 4% of the radius, the orbital radius that Mercury is doing, so still quite close to the sun. From there, the spiraling in time would be about the age of the universe. So this also explains the comment, that the question, right? That yes, if you put them far apart, let's say at the Earth radius, and then they spiral around each other, yes, they'll stay there happily forever, literally, almost literally, right? And that's what Kate was saying, that you can have them most things just spiral around each other happily without emitting substantial gravitational waves. Even neutron stars, you need to get them close. So you need to find other mechanisms to get them a little bit close to each other in order for them to start this gravitational spiraling in.
Excellent. So related to this, how are gravitational waves detected?
You want me to jump in?
I think you take that one, Christian. Yeah, you've got more experience than I've got.
So, so the way that you do this is that if you put up two mirrors, you can check, and you send light from one to the other. You can check whether the light is in phase. It's the same thing that I talk about for accelerators, whether the light that comes back to the first mirror is in phase. It has the electric fields pointing the same way as it had the first time it visited the mirror. So what that means is that if you've got light, say from a laser traveling from here to here and back again, you can measure something quite precisely about how far it is. Because if you move the mirror just a little bit, you would lengthen the space, that the length of the track that the light would travel, and just half a wavelength of the light would completely destroy that. It's called interference when it adds up constructively. And that's something you can do. We use it in lasers. That's how lasers work in practice. But it's also used in this type of experiment, except in this case, in the case of gravitational waves, it's not the mirrors moving. It's the space in between the mirrors that's expanding. So they do everything they can to hold the mirrors still, in spite of trucks going past on the highway 2 miles down the road and so on. They do everything they can to keep the mirrors still. And when they do that, they can see space expand in between those mirrors. Right? The mirrors are far apart from each other, kilometers apart. But then they can actually see it. expand in between. That's fantastically cool. Just seeing that equipment blew my mind when I got the opportunity to see some of it.
Thank you. Yeah, so it's something like, I've just looked it up because it's an incredible statement by the experiment. They can measure changes in distance of the order of 1/10,000th of the width of a proton, which is the equivalent precision as measuring the distance from here to the nearest star, 4.2 light years away, to the precision of the width of a human hair. So the precision of this device is absolutely phenomenal. It's a fantastic piece of scientific and engineering achievement, and it's based on very basic principles, like you say, but uncovering.
It's the engineering behind it that's brilliant, right? The physics of it is about 100 years old or something.
Yeah,
few hundred, depending on where you count the start time. But yeah, the technology is, and people didn't believe that it was going to work, right? There were some who thought it was worth giving it a shot, but there were a lot of people who thought this is never ever going to work, because they knew the precision they would require in order to see it, right?
Yeah, it's absolutely phenomenal. Okay, so we'll have one last question, but I'll remind the audience now, if I haven't answered your question or you still have more, you can post them on the forum and someone will get back to you with an answer to your question. So this isn't the end. Please keep asking away. So the last one I'm going to ask this evening, do nuclear explosions use fission? If they do, is there no less violent method to harness its energy?
Okay. I mean, yes, we do. Fission is a thing that happens in stars. Is there no less violent method to harness its energy? I'm not entirely sure exactly what is meant by that question. I mean, are we talking about nuclear power on Earth here?
I suppose if you're strictly speaking about nuclear explosions, you have two options: fission or fusion.
Absolutely.
And fission is typically less energetic than the fusion reactions we talk about. So you can try a different form of nuclear explosion, but chances are you're going to produce a lot more energy, based on what Christian described when he was talking about E = mc squared at the beginning of his talk. You're going to be changing, with a fusion reaction, you will be changing more mass into energy than with a fission reaction. And so nuclear explosions, depending on which one you're talking about, they really come in two forms: fission or fusion, and you don't currently have any other options, any other choices.
Yeah, so there is actually, so just to give a specific example, in the neutron star mergers that Kate mentioned, when the very heaviest elements are produced, actually what happens is that some of those fission come back down, further down in the chart, and then they get recycled back up, and they absorb more neutrons, and they fission again, they come back down, depending on how long they've got in that environment. They might take a few turns and then get back up there. Most of the energy comes from the neutron absorptions, not from the fission.
Okay, so with that, I will thank our two speakers again. I'll bring the Q&A panel session to an end. And once again, I'll say to the audience, remember, you can still post your questions to the question forum on the masterclass website. And thank you all for your questions and participation this evening. The next talk will be this Thursday, and that is going to be related to some of the questions some of you were posting in the Q&A panel. And we're going to be talking about how we can harness some of these reactions that go on in the heart of these astrophysical objects here on Earth for the betterment of society. So in particular, we're going to be talking about fusion reactions, or the speakers will be talking about fusion reactions and how we can use that to produce energy or other benefits for society here on Earth. So with that, I'll bring the session to an end and say thank you all very much, and have a nice evening wherever you are. Bye now.